Section 5.6 is really just a continuation of Section 5.5. So we're looking at the same basic material, finding zeros for polynomial functions. The only difference is we're extending it to complex zeros. So if you remember, or if you watch the notes from the last section 5.5, at the very end, we came across a problem that I mentioned we could go further with if we use complex zeros. So that's what we're getting into here in section 5.6. So you're going to see a lot of the same techniques, a lot of the same types of problems here in this section, but just know that we're taking it one step further. Really the new stuff comes in at the end of the problem once we found all the real zeros using like the rational zeros theorem and synthetic division and those tools we learned in 5.5. Then we look at finding the complex. Then we look at finding the complex zeros for that are left over there. So let's talk about complex zeros, starting with the conjugate pairs theorem. So what is the conjugate pairs theorem? First thing we have here is just a definition of a complex polynomial function. Sorry, I got kind of a little ahead of myself there on the conjugate pairs theorem. All you really need to know is that for all intents and purposes, the functions we're going to be using in this section are the same as the ones we had in the last section. As far as the way they look and feel, they're essentially the same. When we say a complex zero, it still has the same sort of meaning as a zero, like a real zero. That means if you plug it into the function, then you get a zero. Okay. The one big difference, though, that is worth mentioning is complex zeros do not show up as intercepts on a graph of a function. Where the real zeros are always the same as the x-intercepts, complex zeros are not going to show up as intercepts on the graph. So that is one huge difference that we'll see later on as we start working some examples. There's something called the fundamental theorem of algebra, and it's really nothing you need to know or try to learn. Really, it just allows us to do what we're doing in this section, but honestly, you're not going to see it on the homework. It's not going to show up in anything that we're doing. So really nothing to be concerned with. One result of the fundamental theorem of algebra, though, is something we're going to use in this section, and it has to do with how many zeros there are for a complex polynomial function. We said in the last section for a polynomial function having real zeros, you have a maximum number of real zeros that's the same as the degree of the polynomial. And we kind of stressed last time that that's a maximum. It's not a guaranteed number, so you could have less than that. You know, that last problem we worked in the video for 5.5, it was a 5th degree polynomial, and we only found, counting multiplicity, three real zeros. So it's, you know, for real zeros, it's not a guaranteed. It's just a maximum number that's the same as a degree. For complex polynomial functions, we are guaranteed to find as many zeros as the degree. So if it's a 5th degree polynomial, we're going to find 5 complex zeros. Okay, 5 zeros. They may be real or complex, but we will get 5. Okay, so it's always the same as your degree. So that is something good, because you know you're done finding the zeros when you found as many as your degree. So that's what our interest is, finding all the zeros of a complex polynomial function. So the conjugate pairs theorem. This is first little piece that's helpful for us to look at here. The cool thing about complex zeros is that they always show up in pairs. If some complex zero shows up, then what's called its conjugate will also be a zero of that polynomial function. Okay, so what do we mean when we say conjugate? If you'll recall, when we say a complex zero or a complex number, that's a number of the form a plus bi. So if you'll recall, something like 2 plus 3i would be a complex number. And remember that I is the square root of negative 1. Okay, and so we get these complex zeros when we try to do square roots of negatives. So for instance, square root of, I'm sorry, let me back up. The square root of negative 4 would be positive or negative 2i. Okay, so that's when we say complex numbers, that's what we're dealing with, is really square roots of negatives. But here, if a plus bi is some zero of the function, then its conjugate a minus bi is also a zero of the function. Okay, so the conjugate, all we're doing is we're changing the sign of the imaginary part. So if 3 plus 4i is a zero of the function, 3 minus 4i is guaranteed to also be a zero. Okay, so that's very helpful. Kind of a result of that is if our polynomial is odd degree, it has to have at least one real zero. So when we remember we're comparing and contrasting real zeros with complex zeros, since complex zeros always show up in pairs, if it's an odd degree polynomial, we're guaranteed to have, say, 5. If it's a fifth degree, that'd be 5 zeros. If the complex ones show up in pairs, that leaves one kind of hanging out there to dry. That fifth one that's not complex will be real. So that's basically what this is saying. If this is our function that's fifth degree, it's got at least one real zero. All right, so here's an example of something you might see on the homework. We've got some information about a polynomial whose coefficients are real numbers. Find the remaining zeros of f. So it's a fifth degree polynomial, and the zeros are 1, 5i, and 1 plus I. So we want to know what are the remaining zeros. Well, those are just going to be the conjugates of the complex zeros. We've got two complex zeros here. The conjugate of 1 plus I is 1 minus I. That one's pretty simple. The conjugate of 5i, now be careful. We said for that we change the sign of the imaginary part. So it becomes a minus 5i. So those are the remaining zeros of f. Just as an addition, if we wanted to write out that function, actually what it would look like, which is not required for this problem, but you will have to do this eventually, so let's kind of practice it a little bit here. If 1 is a 0, x minus 1 is a factor. If 5i is a 0, x minus 5i is a factor. Works just the same. If minus 5i is a 0, then x plus 5i is a factor. Where it gets tricky is if 1 plus I is a 0, then x minus 1 plus I is a factor. The same thing for 1 minus I. So because there's two terms in those factors, you kind of have to put some extra parentheses in here around those because we have to subtract that value. So you actually end up with x minus 1, x minus 5i, x plus 5i. Distributing the minus sign gives you x minus 1 minus I and x minus 1 plus I. Okay, so that's something you will have to do in some other problems later on. So there's an example. But for this one, all we needed were those two answers right there. That was the answer to this problem. Same question here. Degree 4. We've got zeros of 1, 1, and negative 4 plus I. So the remaining zero would be, change the sign of the imaginary part, negative 4 minus I. Done. Okay. Example 3, kind of diving right in here. Find the complex zeros of this polynomial function and write the function in factored form. So we're going to use all the same tools, all the same things that we looked at in the last section as far as finding zeros. One of the easiest things to do is just to start with a graph. Maybe just look and see what the graph looks like. So 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. And here's our graph. Okay, so what do we got going on here? Looks like we do have two x-intercepts. I believe the left one is at -2, the right one, gosh, that's hard to tell. So let me calculate that 0. And this might be tricky to do. Okay, there, I'm on the left side. It's pretty steep, so. And there I'm on the right side. 0.3 repeating, so that would be 1/3, right? So x-intercepts at -2 and at 1/3. So let's hit that synthetic division. Starting with -2, it's 3x to the 4th, 5x cubed, 25x squared, 45x, and -18. So bring down the 3, multiply, you get -6, add, that's -1, multiply, that's at +2, which is 50. -2 and 50 is -100. Something's not right. Well, that didn't come out well at all, did it? So maybe, so we get a remainder of 92. Did I make a mistake anywhere? Whoops. Looks like I forgot to add. See, one little mistake in your synthetic division, and you may realize this by now, can cause mayhem later on down the road. But get that fixed, and there we go. There's that remainder of 0 I was looking for. And let's do our 1/3. Now, can we do synthetic division with 1/3? I say, why not? It's really just multiplying and adding, right? So bring down the 3. 1/3 of 3 is 1. Add that, we get 0. 1/3 of 0 is 0. Add, we get 27. 1/3 of 27 is 9. And add those, we get 0. So yeah, we can do it with 1/3. That's no problem. And so up till now, here's what we're dealing with. We've got our function. We factored it. We know that x plus 2 is a factor. Because -2 is 0, we know x minus 1/3 is a factor because of 1/3 being a 0. And then we're left with, okay, this was x to the 4th, and then x cubed. So this is x squared down here. So that's 3x squared, no x term, plus 27. So we found two real zeros. We know this is a 4th degree polynomial. So there's got to be two more complex zeros left. And they're going to lie inside this piece right here. So to figure this out, take this and set it equal to 0. And actually, before we do that, we can, let me back up here. Sometimes it's good if you can do any factoring on this piece to go ahead and do it. So in other words, I can factor a 3 out of that. So this 3 can be factored out front and gives me x squared plus 9. So I can do that. And now let's do what we were going to do and set that equal to 0. So from here, it's just a process of solving this. We can subtract 9 from both sides and then take a square root. And here we have plus or minus the square root of -9, which is 3i. So those are my other two zeros. So I can finish this then by saying 3 times x plus 2 times x minus a third times x plus 3i times x minus 3i. So there's my factored function, and my zeros are negative 2, positive 1/3, 3i, and negative 3i. Okay, so there it is. So you see it's almost the same as what we did in 5.5. The only new thing is really that right there, is setting up that equation and solving it for that complex part, plus minus 3i. And again, I want to reiterate, that did not show up on our graph. We don't have any intercepts at 3i. As a matter of fact, there is no 3i on that graph there anywhere. Those are only real numbers. So you're not going to find these complex zeros on your graph. You have to go through this process of factoring it out and then setting up an equation to solve to get the last complex zeros. So let's do another example. Again, start by looking at the graph. It's always a good place to start. Find the real zeros. So x cubed plus 13x squared plus 57x plus 85. So what do we got? We got a little touch and go. Is that at negative 5? Okay, so let me just double check. Whoops. If I trace and go to negative 5, yeah, there's the 0. So let's start there with our synthetic division. We have a 1x cubed, 13x squared, 57 and 85. Try not to make any mistakes this time. Okay, so there's a remainder of 0. Multiply and add all the way across. So my function then is x plus 5 times, this was x cubed. After one round, this is x squared plus 8x plus 17. So I found my real 0. I know negative 5 is my one real 0. Now I've got to look at this piece right here and say, okay, can I solve this equation? Can I find out what the zeros are there? Now for this, we can't just move a term to the other side and take a square root like we did on the previous examples. Not quite that easy. We can't factor that at all. We're going to have to rely on this guy right here. Remember this is the quadratic formula. Okay, and this is something that you got to use from time to time on these. If you can't factor it or anything like that, then it just falls back on the quadratic formula. We need to know the values of a, b, and c. So remember, this is a, x squared, b, x, and c. So a is 1, b is 8, c is 17. Notice that's the same as, this is a, b, and c on that synthetic division, just those coefficients. So we would say the opposite of 8 minus 8 plus or minus the square root of 8 squared minus 4 times 1 times 17, all divided by 2 times 1. 2a. So that is negative 8 plus or minus 64 minus 68 over 2. Just work this down. We get negative 8 plus or minus 2i over 2, which will reduce. Okay, negative 8 over 2 is negative 4, and 2 over 2, that just reduces to 1, so plus or minus 1i or I. So there's my other two zeros. Negative 4 plus I and negative 4 minus I. So let's go all the way back up here. It was x plus 5 and then I've got x minus, having issues here, minus negative 4 plus I and x minus negative 4 minus I. So make sure you get all those parentheses in there like they need to be. So if we distribute some negative signs, we get x plus 4 minus I and x plus 4 plus I. For my factored function and my list of zeros is negative 5 and negative 4 plus I and negative 4 minus I. Alright. So that's complex zeros. Again, almost the same as finding real zeros, but you got that last little bit where you have to go back and either use the quadratic formula or maybe it's a little bit easier where you can use that square root method to get your solutions. But all in all, that's it. That's section 5.6. Nothing really new per se, just taking it a little bit further and finding those complex zeros.